Hey guys, we are wrapping up bonding today and we are going to talk about the 3 different types of bonds. We're going to review ionic bonds, covalent bonds, and then talk briefly about metallic bonds. So as you can see, I have my writing utensil, I'm using a pen, and I have 2 additional colors, and I have my scissors because we are making a foldable and we will be using these colors to label. So, as usual, I take my sheet of paper, I fold it in half, long ways, hot dog style, so it looks very narrow. Line up my edges and flatten it so it looks like this. Doesn't have to be perfect, it just has to be efficient. So once I have this, I can take it and fold it over into thirds, so that I have my 3 sections. Again, does not have to be the prettiest thing in the world, just needs to be efficient. Alright, this and flatten. Hopefully the camera doesn't shake too much. Alright, so now I have this piece right here, so that when I unfold it, I have it in thirds, and now I have it when I completely, there we go. When I completely unfold it, I have 6 different pieces. I'm going to take my top 3 pieces right here and cut along these lines so that I have 3 flaps that fold up. So take my scissors and cut. Take my scissors and cut all the way up to the centerpiece, so that now I have my wonderful 3 flaps, and I can fold them up so that I have nice 3 distinct sections. Alright, so these are the 3 different sections that I talked briefly about, and we are going to start off using my writing utensil. We are going to start off talking about ionic bonds. Alright, so our first flap labeled ionic bonds, you lift up the flap, and on the top part of the flap, this is where we're just going to do some general information that we already know about ionic bonds. So for example, I'm going to go ahead and take my first colored pen. I'm going to use blue in this case. So green is my backup. So ionic bonds are between metals and they are between nonmetals. Alright, so if I have a metal and if I have a nonmetal, that is what makes an ionic bond. So say, for example, I have calcium. Calcium has a chemical symbol of Ca. It has 2 valence electrons, and it has decided that it wants to bond with chlorine, Cl. Chlorine, we know, is in group 17, so it has 7 valence electrons. Having only 7 valence electrons, it is really, really close to having 8. It's close to having a full octet. So, chlorine has decided that it wants to snatch one of the ones from calcium. So one of the electrons is going to come off of calcium and onto chlorine. But calcium still has 1 more electron that it wants to get rid of. So a second chlorine atom is going to come in with its 7 valence electrons, and it is going to steal that last electron off of calcium. Now, when I do this, or when this happens, my calcium now has a +2 charge because it lost 2 electrons, it lost 2 negative charges, and each of my chlorines, so for every 1 chlorine, it gains 1 electron. It gains 1 negative charge. And when that happens, I end up having to have 2 of them. So if you will recall, I used my crisscross method to take the value of each of my charges, drop it down, so that I have Ca1 Cl2 as my formula. And I have my metal and my nonmetal to make an ionic bond. So, talking about some of the different properties, moving into the main section, some of the different properties of network structures, or of ionic bonds, is that they have network structures. Okay, so these network structures are very rigid and in place sets of where each atom goes. It has a very distinct location. So for example, all of my calcium ions are going to be lined up like so, all nice and neat and in rows on top of one another. My chlorines, however, are much, much smaller, so they are going to come in, and then they're in between. They're still bonded to the calcium, but they fill in these empty gaps right here. And with how everything, it's like when you stack sheets of paper, everything just lines up so nice and neatly. It's the same thing with these network structures. And so there's all my little chlorine pieces. Now, because these guys are in such rigid structures, they don't like to break apart very easily. And so in order to break apart, you need a lot of energy. And one of the forms of energy that we've talked about is heat. So I can add a lot of heat to break these bonds, which means that they have high melting points. Hi, honey. So, with these high melting points, it requires a lot of energy, a lot of heat to break these bonds. But when we do break the bonds, we talked previously about how they're made of ions. So these ions mean that electrons are easily moved. So going back up to the top, the reason ionic bonds work so well is because they transfer electrons. So the transfer of electrons are a key piece to ionic bonds. So these transfer of electrons mean that they can conduct electricity really well. So they can conduct electricity because of this transfer of electrons. And the final piece is, with our different ions, we've also talked about polyatomic ions. Okay, and we said that polyatomic ions were a group of covalently bonded atoms that act as one ion. So polyatomic ions are a group of covalently bonded atoms that act as one ion. And that is everything that we need to know about ionic bonds. Moving forward, the next piece that we talked about were covalent bonds. Okay, so covalent bonds. Now, when we're talking about covalent bonds, we said that covalent bonds were between two nonmetals. So whenever I have a non-metal and a non-metal, those are covalent bonds. And unlike ionic bonds, they don't transfer electrons. Instead, they want to share electrons. So they have shared. I apologize for that funky C. They have shared electrons. And when it comes to covalent bonds, there are two different types. We have two different types of covalent bonds because the electrons are not always shared so nicely. So the first type of ionic bonds, let's go with our first color, we'll go blue. So the first type is polar covalent bonds. If I were to divide this section in half, all right, so my first type is a polar covalent bond. This is when electrons are shared unequally. So I have, let me get my blue, electrons, I'm abbreviating, so electrons shared unequally. Okay, and say for example, I have hydrogen. It has one valence electron, and it has decided that it wants to bond with bromine. Well, bromine is in period or group 17, so it has 7 valence electrons. And in order to be happy, it needs one more. But hydrogen is really reluctant to give up its one electron, and bromine definitely doesn't want to give up one of its electrons. So instead, they both have agreed, they've made a pact, that they are going to share one of their electrons. So now, hydrogen in its first outer shell has 2 valence electrons, which is all that it needs to be happy. And then bromine also now has 8 valence electrons in its outer shell, so it is also a happy camper. And then if you were to write out the chemical formula, that would be HBr. And they're pretty content like that. They don't mind sharing with one another because they have their own full valence shells, and they're okay with that. But what happens is we see that bromine has a lot more electrons. Even though it's only sharing one, it's still partially getting one from hydrogen, and hydrogen is partially giving its one away. So bromine has a slight negative charge to it, and hydrogen has a slight positive charge to it. Now, these partial charges are what we call dipoles. So a dipole moment or dipoles are partial charges where I have a partial negative charge and a partial positive charge. And I connect my plus to my minus and then add an arrowhead. And this will show me that my dipole moment is moving towards bromine so that I have the electronegativity is moving towards bromine. Opposite of a polar is a non-polar covalent bond. Now, this is when electrons are shared equally. So this time electrons are shared equally. So because they're shared equally, I don't have a partial charge. So let's look at fluorine, for example. If I have fluorine, it has 7 valence electrons, and it wants to have one more. So if fluorine were to come over and bond with itself, which also only needs one more, if they both decide to agree and share one from their outside, so my first fluorine is sharing one and my second fluorine is sharing another, they now both can have a full octet. And they both are sharing the same amount of electrons, so there is no partial charge to it. If I were to write the molecular formula, well, it's just F2. Which leads me into reminding you guys about Brinkelhoff, my personal favorite. These are the different diatomic elements. So I have Br, I, N, Cl, H, O, F. These are your 7 diatomic elements, Brinkelhoff, that whenever we naturally find these elements, we are always going to find them bonded to each other, like this fluorine here. Another way to remember it is that I have no bright or clever friends, which I know that is so very true in my life. Hopefully you guys have brighter friends than I do. So, moving on to the different properties of covalent bonds. So we talked about ionic bonds having network structures. Well, covalent bonds form molecular structures. So they form molecular structures. So we've talked about water, for example, H2O being a polar molecule. So if I were to take H2O, I'm going to take my oxygen, and it goes in the middle. And oxygen has 6 valence electrons. And yes, I know I'm drawing them a little different. It's okay. You'll see why here momentarily. So I have my oxygen, and I have 2 hydrogens. So keep in mind that this small subscript after the element tells me how many I have. My number comes after the element. So I have 2 hydrogens. So the first one is going to share its 1 electron on one side of oxygen, and the other hydrogen is going to share its electron on the other side. And I have 2 what we call lone pairs, because it's a pair by itself. It's a pair of electrons by itself. We'll go more into that later. But I have 2 lone pairs off to the side. And if I were to draw how these are covalently bonded to each other, I end up having something that kind of looks like a Mickey Mouse. So see, I got the head and I got my 2 little ears. So I have my Mickey Mouse, and that is my water molecule. But we talked about hydrogen having a partial positive and oxygen having a partial negative. So when I connect these 2 lines and draw my arrowhead for both sides, then we can see that when we go down towards the oxygen, this entire lower half down here is more negative, but both ends of my hydrogen are now positive. So when I have ice that forms and it wants to be more structured than just a liquid water, these positive ends of the hydrogen are now attracted to negative ends of oxygen for different atoms. In addition to these molecular structures, it's possible for us to have a different number of bonds. So this right here, where I have only 2 electrons being shared, that's called a single bond. So I can have a different number of bonds. And the first type is a single bond. So the first one is a single bond. And say I have my 2 hydrogen, and one will donate 1, and another hydrogen will donate another electron. Every time I have 2 different electrons from 2 different elements next to each other, I'm going to redraw that so that my hydrogens now have a line between them. And this line right here represents these 2 electrons. And that is a single bond because I have 1 single line. Now, if you're single, you can also have a double. You can also have a double bond. And so say for example, I had 2 oxygen that were bonding together. Well, oxygen have 6 valence electrons. So I'm going to draw 4, 5, 6 for one. And yes, I know they're not grouped like we normally do. You'll see why momentarily. I can take my other oxygen, which also has 6 valence electrons. And so now I have 2 sets of lone pairs. Alright, and that is why we don't try and MacGyver our way with a whole bunch of stuff. Honey!
I heard it crash.
Technical difficulty, students. Give us one moment. We'll edit this out later. If you can find the whatever that was. The counterweight, that's what that's called. Curse me in all of my writing. Hey! I'm just gonna make that a little more steady. It's probably part of the problem. Let's make that a little more even. Alrighty, and we are back, ladies and gentlemen. Thank you, babe! You love me. Alright. He's mine. Alright, so going back to the oxygens. So I have 2 oxygens, and you can see now I have 4 electrons, 2 on the top, 2 on the bottom. So I can redraw my oxygens with 2 lines in between them. And this means I have 1, 2, I have double bond. And then draw in my extra lone pairs of electrons. And last but not least, it is entirely possible to have not a single, not a double, but a triple bond. So I have my triple bond. And this time I'm going to use nitrogen as my example. So my first nitrogen, it has 5 valence electrons, so I'm going to put 2 on one side. And I'm actually going to draw this one slightly different. I have 3 coming off to one side, and then I can have a second nitrogen that will also donate 3 of its valence electrons, while it has 2 as a lone pair off to the side. And because I have these 3 right here, it gets a little funny to draw it like this, so we're gonna redraw it instead, where we have 3 horizontal lines. And so those are my 3 triple bonds. Now, because we can have so many of these different bonds, and because these electrons are being shared, it's okay for these electrons to kind of shift around a lot. And so because these electrons are shifting around, it doesn't require a lot of energy to move them. So we talked about energy also being in the form of heat. So if I were to take a covalently bonded molecule such as sugar that we worked with, which is C6H12O6, all are nonmetals covalently bonded together, it requires a low melting point. So a low melting point meaning it does not require a lot of heat to break these bonds apart and to break down the molecular structures. Also, when we've talked about properties of just nonmetals in general, nonmetals don't like to conduct electricity. So molecular structures are the same way. They don't conduct electricity. And that is everything we have in review for covalent bonds. So that covers everything that we've talked about so far. Monday with covalent bonds, Tuesday and Wednesday with ionic bonds, and just a little bit of review in the middle. So I'm running out of room because I want to keep this nice and centered for you guys. And the last piece that we haven't really touched on and is just kind of thrown in there but really important to talk about are metallic bonds. So metallic bonds is my last piece. And don't freak out, I just took my ionic bonds and I flipped it under so that you guys can see the metallic bonds in the center. So if I take my metallic bonds and flip it up, so we have metals and nonmetals for ionic bonds, and then we have two nonmetals for covalent bonds. Take a guess at what metallic bonds are between. Yep, you guessed it. It's between two metals. I'm so proud of you guys. I knew you would get this one. So if I have a metal bonded with another metal. Now, because of this, we've talked about how metals have lots of luster. They're very ductile, and they're very malleable. What this means is, say for example, I have a copper wire. This is the easiest way for me to show it. So I'm gonna draw out a copper wire, but I'm gonna zoom in a little bit. So this right here is the outside insulation. Everything here in the middle is going to be the actual copper wire. So I have my insulation on the outside, right? So I have a bunch of copper atoms here, through and about, just kind of all bunched up together in nice, neat little structures and patterns. And one more right there, all right? So copper, we know, if I can grab my periodic table right here, copper is, where did it go? Right there, there's copper. And we can see it's right here in the middle with our transition metals right here. And we said that transition metals are special because they can give off a different number of electrons. They don't have any one set charge. So because of this, whenever I run an electric current through, an electric current is nothing but a movement of electrons. So all of these dots that I'm drawing right here are a bunch of electrons. And of course there's more copper atoms in here, but I'm only drawing a few. So all of these electrons are being moved through the copper metal wire. It's going to end up looking like a watermelon with all these little dots. Okay. So just going through, drawing all these dots to represent all of the different electrons that could be through here. Now, when I'm running a current, I'm running more and more electrons, and these electrons, they don't have any one particular spot. They're kind of attracted to the copper, but with all of the extra electrons and all the extra shells, not so much, so they move very easily. And what this ends up doing, and this creates a sea of electrons. So I have a sea of electrons. All of these electrons are kind of like waves. They're just kind of going with the flow and they're being pushed through when they need it. So just to label a few things, is this whole thing right here is a copper wire. Just a bunch of copper atoms. This right here is an actual atom. But all these tiny little dots right here are my electrons. Okay? So, just some properties moving down to that bottom section. So, what we just talked about with our sea of electrons is that transition metals are willing to share their valence electrons. So transition metals are willing to share their valence electrons, and they're willing to share more than one valence electron if they so need to. So when this happens, electrons break off and flow and I'm abbreviating between. So electrons break off and flow between atoms in a quote-unquote sea of electrons. So with all these electrons moving about, anything that is a moving object, we call it mobile. So these mobile electrons, electrons that are moving about, So these mobile electrons cause the luster of metals. So they cause the luster and conductivity. So all of these electrons moving about are what cause the luster or the shine of metals, and it is what conductivity is. Conductivity is a current of electrons. Current because currents are in the sea and whatnot. So that's actually where we get that term, is because we have the sea of electrons, so that's why they call it a current. Not really, don't quote me on that. So, because of all of this, metallic bonds don't break. Metallic bonds don't break. This is why it's so easy to make aluminum foil or to have copper wires. Because the metal bonds don't break, we can shape them into wires. We can shape them into a variety of different things to fit around a car to help support beams. They don't break very easily, so they're very sturdy. And with the conduction of electricity, it is extremely helpful with the modern age and all of the technology that we use. So, this is everything that we have for ionic, covalent, and metallic bonds. These are the 3 different types of bonds. And then flipping up so you can get a decent screenshot of all of these. So these are all of my upper flaps right here. And then I have all of my lower flaps talking about all of the different properties. And that is it. So thank you guys for watching. I hope you enjoyed and have a wonderful rest of the class period. And I hope you guys have a wonderful weekend. And I'm so sorry that I couldn't be there. Love you guys.